So let's look at an example so we have a concrete example of what exactly is done when constructing a confidence interval. A sample of 36 NCC students has a mean GPA X bar of 2.63. Assume that the population standard deviation, sigma, is 0.6. These are things that need to be provided to you before starting a confidence interval problem. You need to be told the sample size, you need to be told the sample mean, and you need to be told the population standard deviation. Okay? We're going to construct a 90% confidence interval for estimating the population mean GPA of NCC students. This question is asking us to find an interval of values for which we are 90% confident the true population mean GPA lies. Okay, so this sample GPA is not the true population mean GPA of all NCC students, but we're going to use it to try to come up with an estimate for what the real true population mean is. And we want to come up with an estimate with 90% confidence or 90% certainty. The true mean GPA is probably not 2.63, but we can build a range of values around 2.63 that contains the true mean with 90% certainty. So let's say there's a horizontal axis of all GPAs. Okay, so all the GPAs are listed here from low to high, and somewhere over here we have the true mean mu GPA. We don't know what it is. Over here we have our sample mean GPA, which came out to be 2.63 because we have a sample of 36 students. We found all their GPAs divided by 36, and we got an average of 2.63. If we can construct a range, look at this yellow bar that surrounds the sample mean. It's a range of values around the sample mean constructed so that it captures the true population mean. So the yellow box provides a range of values around the sample mean. And that's our goal in creating a confidence interval. We want to create a range of values around the sample mean that captures the true population mean. Now, it may be the case that the true mean is over here or over here, and that our yellow box fails to capture it. Now, that's going to happen if we construct a 90% confidence interval. That's going to happen 10% of the time, that the true mean is going to fall outside of the yellow box. So our goal is simply to create a yellow box with 90% certainty. So with 10% chance that it does not fall within that box. The interval that we create, which is the yellow box, may or may not contain the true population mean, but we will be 90% certain that it does. Start with a picture of the sampling distribution of the mean with the true population mean GPA unknown in the center. So let's look at the sampling distribution. Remember that sampling distributions have on their horizontal axis possible sample means, X bar. In the center, we're going to put the true population mean mu, which we currently don't know. We don't know what that value is. We just know the center is in the center of the bell curve. On the horizontal axis, we have possible sample means for the sampling distribution. The center 90% of all possible sample means are shown here. The x's represent, or rather the x bars, represent just some possible sample means. Our sample mean can be any point on the horizontal axis. Okay, so our sample mean can fall anywhere on the horizontal axis. We got a sample mean of 2.63, and it could be anywhere. If an interval, the length of the red arrow, is constructed around every possible sample mean, exactly 90% of those intervals will contain the population mean, and 10% will not. Here's an example of what I mean. Let's suppose that this X bar over here in the bottom 5% of area, this X bar was used to estimate the true population mean, and an interval of values, the length of the red bar, was constructed around X bar. We'll take a look at where it falls. On the left-hand side, it falls way down here. On the right-hand side, it falls just short of center, the true population mean mu. So let's remember, the true population mean mu is in the center here. We want our red arrow to basically capture that true population mean. So sometimes it will, sometimes it won't. It does in this case. Notice how here's the center, here's the red arrow, it captures the true population mean. This one is okay. This sample mean is also good. This sample mean is good. This sample mean is good. This sample mean, too far off to the right. The red arrow falls short and does not capture the true center, the true population mean. And the last one is also too far off. It won't capture the true population mean. So, coming to a conclusion about this, any X bar that falls within the center 90% of the bell curve is going to be okay. And any X bar that does not, that falls in the bottom 5% or the top 5%, is not going to be okay. And that's why we say exactly 90% of those intervals will contain the population mean and 10% will not. So let's suppose for the time being that our X bar happens to be here relative to the center of the distribution right there. We find the 90% confidence interval with the following formula. X bar, that's the sample mean, minus 1.65 times sigma divided by the square root of n. That's the lower end of the confidence interval. 2, X bar plus 1.65 times sigma divided by the square root of n. Now, remember that in the beginning of this lecture, we found the z-scores that cut off the middle 90% of all z-scores. We found it to be negative 1.64 and positive 1.64. I know these z-scores are not exactly the same, but I'm following what the textbook does. So if you use the textbook to follow along with these examples, you'll find that it uses negative 1.65 and positive 1.65 in this formula. So I am keeping with the textbook's convention. And here, sigma divided by square root of n, we have something that's familiar. It should look like the standard error to you. So we have X bar minus z times the standard error to X bar plus z times the standard error. Now in our problem, X bar is 2.63. The standard deviation is 0.6. The size of the sample is 36. So we have 2.63 minus 1.65 times 0.6 divided by the square root of 36 to 2.63 plus 1.65 times 0.6 divided by the square root of 36. So I'll show you how to do this on the calculator, but it should come out to 2.465 to 2.795. So you have 2.63 minus 1.65 times sigma, which is, again, 0.6, divided by the square root of 36. Okay, so this first part is the lower limit of the confidence interval, 2.465. Now, to do the next part, all we need to do is change this negative, this minus sign, to a plus. So we can just repeat that previous entry. Hit second and then enter. It's going to repeat that previous entry. Scroll over and change that minus to a plus. And then 2.795 on the right, or the upper entry. So that's how we arrive at our confidence interval. So we have to remember this formula. X bar minus 1.65 times sigma divided by the square root of n to x bar plus 1.65 times sigma divided by the square root of n. That is the formula for a 90% confidence interval. And when we're asked to interpret the confidence interval, we're going to say something like the following. We are 90% confident that the true population mean GPA of all NCC students lies in the interval from 2.465 to 2.795. Okay, so we have to say when we arrive at these range of values, it's not absolute certainty. So we have to say exactly how certain we are that it's correct. We're 90% confident because we found a 90% confidence interval. What makes a 90% confidence interval different from a 95% confidence interval or a 99% confidence interval is the use of the z-score. We're going to change the z-score for different confidence levels. Okay, so for a 90% confidence intervals, the z-scores are negative 1.65 and positive 1.65. When asked to construct a 95% confidence interval, you're going to use z-scores of negative 1.96 and positive 1.96. When asked to construct a 99% confidence interval, you'll use z-scores of negative 2.58 and positive 2.58. And so the formulas are as follows. The 90% confidence interval, as we saw on the previous slide, is this one. And with a 95% confidence interval, you simply change the z-score from negative 1.65 to negative 1.96. Positive 1.65 to positive 1.96. And a 99% confidence interval, we just change the z-score negative 2.58 and positive 2.58. So these z-scores, these formulas generally are the same thing except for changing z-scores. So that's how you change between a 90% confidence interval, 95% confidence interval, and a 99% confidence interval. So you should take note of what happens when you increase the z-score. Rather, well, actually, what's happening here is we're spreading out the z-scores further away from center. When you spread out the z-scores far away from center, you're increasing the range of values. You're increasing your range, so your lower limit gets smaller and your upper limit gets larger. With an increased range, with a greater range, you have greater confidence. So the range for a 95% confidence interval is going to be smaller than that of a 95% confidence interval. You increase the range, you increase the confidence.